Assalamu alaikum. Dear students, I am Tahir Yusuf from JK College. Today we are going to discuss second year chapter 11, and the name of the chapter is electrostatics, and our topic is Coulombs law. This is the first topic of this chapter, electrostatic. So first you know about what is charge. You study in 10th class, the charge is the intrinsic property of the matter. There are two types of charges, one is positive and one is negative. There are two types, positive charge and negative charge. So Coulombs measure the force between two electric charges. Well, this is the first discovery. It means these are like charges, positive, they repel each other, positive and negative, they attract each other. So Coulomb first discovered the force between two charges, which is positive or which is attractive or which is repulsive. So he used apparatus for this measurements, or for this law, or for this detecting of force is called torsion balance. He used torsion balance apparatus for detecting this force. So Coulombs gave a statement. He said that if we have two like charges, like I have two positive charges, one name is Q1 and other name is Q2. These two are point charges. They both repel each other. It means Q1 repels Q2, and we denote this by a force F12, and if Q2 repel Q1 charge, we denote this by a force. So force is a vectored quantity. If Q1 applies a force Q2, the Q2 charge repels in the same direction with a unit vector R12, and if Q2 repels Q1 charge, it's also in the same with applying force. So R21 is also a unit vector for Q1. This is a displacement in this direction, Q1 displaces, and in that direction R12, Q1 applies a force and Q2 displaces. So Coulomb states that the force which is attractive or repulsive, we denote this attractive or repulsive force, this force is directly proportional. If these two charges are larger, so the attractive or repulsive force is also large. If these two charges are small in nature, so the attraction or repulsion of these two charges is also small. So he said that the force of attraction or repulsion between these two charges is directly proportional to the product of these two charges. It means the product is large, the force is large, and if the product is small, the force is small between. This is attractive or repulsive force. He also said that if the distance between these two charges, let we denote this distance by R, if the distance between these two charges is large, the force is small, and if the distance is small, the force is large. This force is all attractive or repulsive. So he said that the force of attraction or repulsion between two charges is inversely proportional to the square of the distance between them. That we can write mathematically. This is a mathematical form of the Coulomb's law, and the statement will be the force of attraction or repulsion between these two charges is directly proportional to the product of these two charges and inversely proportional to the square of the distance between them. This follows inverse square law. So for that purpose we use R square. If we combine the equation 1 and equation 2, it will be Q1 Q2 over r square. You know, if we remove this proportionality sign, we use equality. It's mean for this, here we use f is equal to, if we remove proportionality sign, we use two. One equality sign and the other is proportionality constant. We use these two terms for removing proportionality sign. So this general equation A is called the Coulombic or electrostatic force between two charges. So first we are going to explain this K. This is called proportionality constant, and the value of K is 1 over 4 pi epsilon naught. This epsilon naught means permittivity of a free space. It means for this experiment we use a medium like air. So for free space we are using permittivity of free space. The value of this is epsilon naught is equal to 8.85 into 10 raised power minus 12 Coulomb square per Newton per meter square. If we put this value in above equation, so the value of the K, if you put the value of 4 and the pi which is 3.14 and the value of epsilon naught, so the K will be 9 into 10 raised power 9 Newton meter square per Coulomb square. So this is the value of K constant. We use in numericals direct this value by the value of K. So we in numericals we know the value of the value of Q1, Q2 and R given, and we are going to find the value of force. So the K, we remember this value. This is very important value. And the value of K, on which factors the value of K depends? The value of K depends on two factors. K depends on two factors. Number one, the medium. In which medium these two charges are placed, and the system of units. The second one is systems of units, in which system we describe force Q1, Q2 and R. If in SI system the value of K is different, in other system the value of K is different. So the K is depend on the medium between these two charges. We place air, we place vacuum and other substances like glass, so the value will be changed. So this is the Coulomb's law, and the formula of the Coulomb law is F is equal to K Q1 Q2. So now we find the value of force. This is the Coulombic force. Now we are proceeding towards pointing the direction, how we use this value. Let's suppose for F12 force we use K Q1 Q2 over R square, and this is in the direction of R1, 2. If these two charges are like charges, means these two are positive charges, so the force will be F12. The resultant force will be a positive, and this force will be a repulsive force. And if the charges are unlike, means this is Q1 and other is negative point charge and this is Q2, so the force is attractive force between these two. So for this, for unlike charges, we use F21, which is equal to K Q1 Q2 over R square in the direction of R21. It's mean Q1 for F12 means Q1 applying force on Q2, and this both charges are applying towards each other. So these by Newton's third law, and we can say that the equation 2 and 3, we can write this equation. These two are F12, this is equal but opposite in magnitude to F21. And if these two forces are equal and opposite, so their unit vector R12 is also equal and opposite to R21. So this is by Newton's third law. We can say that R12 which is equal and opposite, and if these two forces are like in diagram 1, Q1 and Q2, so their position vector R12, and the F21 force is their position vector R21. So this is the Coulomb's law. We use this force is a vector quantity, so we can write the vectorial form. If we can write vectorial form, so the vectorial form means the vector form of Coulomb's law is F. This is a vector form, K Q1 Q2 over R square, and this is a unit vector. If we place a unit vector, so this equation is called, this formula is called, this is the vector formula of the Coulomb's law. So Coulomb measured the quantitative measurement of the electric force between two charges. So this force is called electrostatic force, or this is also known as Coulombic force. Thank you, students.
Start.
Now we are proceeding towards Coulomb's law in material media. We consider two point charges Q1, and the other is also a point charge, positive point charge, and the separation between these two charges is R, and the force is F12 and the other is F21. If we write equation Coulombic force, which is equal to F is equal to K Q1 Q2 over R square in the direction of R. So in this value of K, 1 over 4 pi epsilon naught. Epsilon naught, we can write this epsilon naught is a permittivity of free space. So if we write this equation of force, which is equal to F is equal to 1 over, we put the value of K in above equation, 4 pi epsilon naught Q1 Q2 over R square in the direction of R. If we want to use a medium between these two charges, so what should we do? We use another term. Here we use another term Q1 Q2 or R square in the direction of R. For if we use vacuum between these two charges, the value will be 1, and if we use air for this value, so the value will be changed and the whole calculation will be changed. So for this we use the permittivity of free space, or which is used we use epsilon R is equal to epsilon over epsilon naught. This formula will be used, and for this purpose at the end, the ending value of this is we can write here epsilon naught, which is permittivity of free space. This is also permittivity of free space, and when we multiply epsilon naught is equal to epsilon naught. This is called the permittivity of the medium. This is called the permittivity of the medium. So this is the permittivity of the medium. For permittivity of medium we use epsilon R. So this one for epsilon R, for vacuum this value will be 1, and for air this value will be 1.006. So the above formula will be given as, this formula will be F is equal to 1 over 4 pi epsilon naught epsilon r for medium Q1 Q2 over r square in the direction of r. If we use vacuum, this is for vacuum and this is for air. If we use vacuum, so the value 1 will be we put the value of vacuum, and if we use these between these two charges air as a medium, so we put the value of air. So on page number 6 there will be a chart, a timetable, that is relative permittivity of various dielectrics. So you can write different values or remember different values for different mediums. So this is the permittivity of free space or permittivity of a medium.
Start.
Students, now we are proceeding towards another topic which is electric field and its intensity. So the concept of field theory was introduced by Michael Faraday. He states, the concept of field theory was introduced by Michael Faraday. He said that when we place a point charge, let's suppose this is Q, or if we are not indicating the value, like you know it's positive or negative, to consider an electric field is produced in a surrounding region. For detecting this field, we use a test charge, which is obviously a positive test charge. The value of a test charge is so small. If we bring close to this test charge to a point charge which is Q, so this charge detects the electric field. If this charge is positive, so the point charge applies a repulsive force on Q naught, and if this charge is negative, point charge is negative, so the Q naught experience a attraction force towards point charge Q. So the explanation of the electric field is, the definition is electric field. We define the electric field by any region, we suppose this region, any region around a charge in which an electric test charge would experience an electric force, and which is this Q naught experience a force, this is the repulsive force, so this Q naught experience a force in that direction. This is that. So the definition of electric field we defined earlier. So again the definition of electric field is any region around a charge in which another test charge experience a force. Another test charge means a test charge experience a force. This is called the electric field or the electric region. It means a negative charge also have some electric field, and if we brought positive test charge, so the attractive force is F towards the balance. If we bring close test charge to the point charge, so the distance between these two charges is small, then the force is large. The force of repulsion or attraction will be large. So if we consider, this is the formula, it means the Q exert a force on test charge. It means the force on a test charge, this is called the electric field intensity. It means this is the vectorial form. This region electric field is also a vector form. So when this Q applies a force on a Q naught, it's determine the intensity of the charged particle Q. It's mean the electric intensity of an electric field at any point is the force per unit positive test charge Q placed at that point. So that we can write this equation by F is equal to Q naught into E. Remember, this is a test charge. So test charge tell us how the electric intensity or electric field is strong. It's mean this Q naught tell us the field is strong or small. So at near end of point charge means at close to the point charges the electric intensity is large, and far apart here Q naught experience a small force. So also intensity depends on the distance between these two charges. Near end, at the closer to the point charge the intensity is large, and at far apart the intensity is small. So we remember this is also a vectorial form. So we can write this equation 1. We can write this equation by, we can use, this is the Coulombic force. So we can write this force is 1 over 4 pi epsilon naught Q naught. So we can use, we have two charges, one is Q and the other is Q naught. So we can write Coulomb's law for these two charges, and the separation between these is R square. So this is the formula of F, and 1 over Q naught. So we can write electric intensity in terms of Coulomb's law. We can place the value of force, and this is 1 over Q naught. So Q naught cancels with the Q naught. So we can only left E is equal to 1 over, we can say this is K, we can write only K Q over R square in the direction of R. Let me explain the last formula. It's mean this is the strength of the field which is proportional to the magnitude of a point charge. Its strength decreases as the test charge moves away from the source. It's mean electric intensity is directly proportional to the point charge and inversely proportional to the distance between point charge and the test charge. Let me explain again. If we have a point charge, so the intensity is large at the closure and at the small distance, and this intensity is small at a far end of the point charge. So this topic is electric field and its intensity. Electric field is a region surrounded by any charged particle on which another test charge exhibit or experience a force. So electric intensity is a force per unit charge, force per unit test charge. So from that we can explain E is equal to KQ over R square. So this is the second formula of this chapter.
Go.
Now students, we are proceeding towards another important topic, which is representation of electric field lines. So electric field is a vicinity of a charged body. This can be represented by imaginary lines which are called electric lines of force, or which is also called electric field lines. So electric field lines or electric lines of force are the path followed by a unit positive test charge in the field of source charge. Let me explain this. If we have a point charge which is equal to Q, and we have a positive test charge, it's also a positive test charge. So we take test charge always as a positive test charge. So these two charges applying a force on each other, which is a repulsive force, if we draw imaginary lines between these two charges, like we can say that Q1 applies a force on Q0 and which is in outward direction. It means this is the lines of force, electric lines of force, or this electric field line. If I change the positions of test charge Q0, like I place Q0 here and change. So this Q applies a force and I draw these by an imaginary lines. Like in every direction you can change Q0. This is also a force. So these arrows indicate the electric field at different points. So these arrows is, these arrows are radially in outward direction. So we can say that electric field lines, so these are imaginary lines, we can say we draw the force or the position of the test charge. These are the always the repulsive force. So these the representation of the position of Q0. So we can say that these electric field lines are originate from a positive charge. Means the electric field line are starting point from a test a point charge Q, a positive point charge. It's mean electric field lines originate from a positive point charge. So if we have a negative point charge, so for negative point charge, this is a negative point charge Q, and we have a test charge Q0. This is always positive. So if I draw imaginary line for these, so between these two charges an attractive force will occur. So the imaginary line will behave like inward direction or towards the negative point charge. If I place in different position or I change the place of Q0, so in every point the direction will be in towards the negative charge. It's mean these are the positions of a test charge. So it's mean if the electric field lines originate from positive, so it's end on a negative point charge. It's mean electric field lines are start from positive and end on a negative. So these are the electric field lines and properties of the electric field lines. If we draw two opposite point charges, so let me explain this. If we have two opposite point charges, one is positive and the other is negative. This is Q1 and this is Q2. So we explain this. Then electric field lines are originate from positive and end on negative. So these are the electric field lines. So these two are point charge. So electric field lines start from positive point charge and end on a negative point charge. You can see that the midline is very linear and the outer lines, the electric field lines, are in circular. This represents that the field is strong in that region. Its intensity is large, and for these its intensity is large. And when the circular line represent that intensity is small, it means the field is strong at that region, inside, and outside the electric field is small or weak. So we represent a curved line for weak forces and a linear or straight line represent the large force or strong field. So let me explain. If we have 2 point charges, same point charges, this is for opposite point charges, and if I represent same point charge, these two are same, it's Q and this is also Q. And next we also explain for same negative charges. These are point charges. This is also Q and this is also Q. We explained earlier, electric field lines originate from positive, so both are same. So electric field lines will be radially outward, and for these two charges, the electric field lines will be at. So for same charges and for positive same charges, the electric field lines will be in that direction, and for negative point charges, for same negative charges, the electric field lines are radially inward, and for opposite unlike charges, the electric field lines are in that direction. If we draw a perpendicular or vector at every point like this, this indicates the direction of the electric field line at that point. So the properties in electric field lines are that they are originate from positive and end on negative, and the tangent at every point gives the position of the electric field line at that position. So these are the characteristics or the properties of a representation of electric field lines. We represent the electric field or the force, the lines of action of force by an imaginary lines called electric field lines. So students, keep watching our videos. Thank you.